In this video, we're going to look at the chemical effects of covalent bond distortion, differences in electronegativity in something that we call dipoles. This is one of these kind of fundamental topics that really carry through all of organic chemistry. So I guess this is a very important lecture as a result. So let's get into it. There we go. Okay, so last time we were looking at covalent bond distortion due to differences in electronegativity. Let's just recap that from a different perspective. So electronegativity, again, I'll abbreviate as EN. So recall the general trend was that H is approximately equal to C, which is less than N, which is less than O, which is less than Br, Cl, I, in that order, which is less ultimately than F. Okay, with that in mind, what we can do is we can start to think about the amount of distortion that we would see if we had two elements bonded. So let's focus on carbon. If carbon was bonded to H, we would see no distortion because they have approximately the same electronegativity. If C is bonded to O, we would see high distortion with a larger orbital area, or because it's in 3 dimensions, larger orbital volume over the element O. Okay, so that's just sort of a recap. What this is going to do is this idea of distortion is this is going to create parts of the orbital that are more electron rich and electron deficient. And that gets into the idea of polarity and dipoles, which could also be called dipole moments. Okay, so if we have, let's look at H bonded to F again, the most extreme example. The molecular orbital that results from sharing these electrons across each of the 2 atoms is distorted, such that there's a larger lobe on the right over the fluorine atom and a smaller lobe over the H. Okay, now what this means is that the electrons are more likely to exist here. Now we think of that as an electron-rich area / volume, I guess. And the smaller volume or area over the hydrogen atom due to distortion is our electron poor / deficient area / volume. Just trying to, I guess, cover all of the possible terms that you would see. Okay, now what this does is this kind of creates an interesting situation for this particular molecule. The electron-rich area is sort of, kind of, maybe, best word, partially negative. That's a really important idea. The electron-rich area is partially negative. Now, why is that? Well, because there's a bigger area or volume of the orbital over the fluorine atom. The electrons are more likely to exist there. The electrons are more likely to exist there. Those negatively charged subatomic particles, which are electrons, are going to create a slightly negative charge. Partial is the word we want to use. Partial negative charge over the fluorine. Note, when I say partial, that's an important word. It's not a full-blown anion. It's not an anion. Okay, an anion is like an imbalance of protons and electrons. It absolutely has a negative charge of at least 1 in increments of 1, all whole numbers. This is sort of a partial charge, we could actually quantify the degree to which it's negative, and it wouldn't be the whole number 1. It would be less than that. In this case, it's heavily distorted, so it might be a little bit closer to 1 than in other cases. So it's partially negative. Now, when we want to show the term partial, this is a fundamental kind of mathematical concept. So partial, I know we like to use the word partial in English, all the time because it's an English word, whatever. Math has adopted this term partial and has sort of given it the symbol delta. This is a lowercase delta, the Greek letter delta. So it's kind of like the Greek letter D in lowercase is going to have this music note looking thing, and that is delta. That's another important idea. Be able to draw deltas. They're not too hard. Delta capitalized is a triangle, delta lowercase is this music note looking thing. So partial. So what we say is that we would say that we have a delta minus charge over the F. That is a partial negative. So we have a partial negative charge over the F. What about the hydrogen atom? Well, the hydrogen atom experiences a smaller area or volume of our distorted molecular orbital that's connecting these two atoms together. So the hydrogen has a smaller area. There's a less likelihood the electrons are going to exist over the hydrogen. So we say that's the electron poor, which matches up with rich, or the electron deficient. You hear that term quite a bit. You never hear electron abundant or electron wealthy or affluent, I guess. I don't know. In the case of electron rich areas or volumes. So electron poor or sometimes electron deficient, though, can describe instances where we have a smaller orbital area for those electrons to exist in over our hydrogen element. Now, what this means is that, let me just make sure I have some parallelism to my notes. What this means is that we have, if we're electron poor, we don't have those electrons to counterbalance the positive charges of the nuclei, as we don't have a greater density of them is the best word I could use. So we have what's called a partial positive charge over the H. Now that's an important concept. In the electron poor areas, we're going to see a partial positive charge. Now, just like before, this is not an ion. In this case, it would be a cation, not a goodness, fumbled here, not a cation. Okay, it's partially positive, not a full positive 1 charge. So it's not a cation. Instead, it's partially positive. We put a lowercase delta plus for partial, and then plus for positive. Okay, so what we can do is we can use these symbols, the delta plus and the delta minus, lowercase, to show the distortion of the sigma bond, or excuse me, the distortion of the covalent bond without having to draw the molecular orbital, which can get cumbersome as molecules get more and more complex. Realize that we're only showing 2 elements in this case, and we want to get to molecules with many elements. So what we would do is we would say, I can recognize that we have a difference in electronegativity, where the fluorine is more electronegative, the hydrogen is less electronegative. More electronegative on the fluorine, less electronegative on the hydrogen. As a result, we have a partial positive charge, or a delta plus on the hydrogen, and a delta minus on the fluorine atom. So what I want you to be able to do is be able to add delta plus or minus to molecules. So if I showed you a very complicated molecule, and there are examples of this in the discussion problem set, I want you to be able to pick out instances where we would have a delta plus or a delta minus. Now, the next thing we want to be able to denote is the idea of a dipole or a dipole moment. A dipole or a dipole moment is a separation of opposite charges. Okay, there's a lot of physical ramifications if you take, if you sort of separate balancing subatomic particles like electrons and protons. So if you separate them in space and you create a slightly positive charge on one side, like the hydrogen, and a slightly negative charge on the opposite side, like the fluorine, you're going to, that separation of charge creates a dipole because we've separated the charge in space. I will even add that, separation of charge in space. Okay, so what we say is that, like, if we take the negative and we put it over here and the positive over here, these opposite charges are separated in space. A dipole forms. So a dipole is formed when we separate our charges in space. Now, we can have a symbol for a dipole. The symbol for the dipole is an arrow with a little line on the tail to make kind of the plus. So to make a plus sign. So this is the positive end of our charges that are separated in space, and this is the negative end. And I remember how to draw this arrow because there's a plus on the tail. Okay, so this is a symbol for a dipole. What this means is that if I have a molecule like H and F, I could draw delta plus and delta minus to show that there's an uneven sharing of electrons in the covalent bond between the two elements, such that the fluorine gets a greater amount of the electrons, a greater electron density, we would say. We would say the fluorine is more electron rich, the hydrogen is more electron poor or electron deficient. Alternatively, what we could do is we could have our dipole arrow, the dipole arrow extending from the hydrogen to the fluorine atom with a positive plus tail on the hydrogen and the arrowhead going towards the fluorine atom. So I remember to draw my arrow because we have that plus table that I align with the partially positive charge of our two atoms that are bonded to making a dipole. Okay, let's practice this. Add 1 delta plus and delta minus to each molecule and draw a dipole arrow. And the dipole arrow again is our arrow where we have a plus tail. So let's take a molecule called chloromethane. So what we notice about chloromethane, maybe I'll write a few of these in case somebody wants to pause and give it a good college try. Okay, so I want to add the delta plus and the delta minus to each of these structures, one, and then I want to add a dipole line. There are instances in this in these examples where you could show a couple of pairs of delta plus, delta minus, and a couple of arrows, and I will typically just ask for one. So what I'll do is I'm stalling so that you can pause the video if you want to give these things a try. Okay, so how do I approach this? Number one, ID the electronegative element. So that's typically going to be your fluorine, chlorine, bromine, iodine. These are my group 7 halogen elements. My O or my N. Carbon and hydrogen are not included. I mean, carbon and hydrogen are more electronegative than some elements on the periodic table. But for the molecules that we're looking at while we study organic chemistry, mostly those molecules contain only carbon and hydrogen. So we don't have to worry too much about any of the other elements. Okay. So what we do is we ID the electronegative element, and it gets the delta minus. So in this case, we have chlorine, which is delta minus, oxygen, which is a delta minus, oxygen, which is a delta minus. Okay. Then we're going to add delta plus to the element it's bonded to. Okay, I know hydrogen is less electronegative than chlorine, but it's not covalently bonded to the chlorine. It does not have to share electrons with the chlorine. It's only the carbon atom that's sharing electrons with the chlorine. It's only the carbon atom that will feel the effects of that electronegativity difference and be electron deficient as a result. Now, there are some multiple bonding effects that's true, but that's more for like down the road. Let's not worry about that. Let's worry about immediate bonding effects. So the oxygen is delta minus. We could put a delta plus on the carbon or the hydrogen atom. Of course, I'm out of room here. And then similarly, we only, similar to the first case, we only have the carbon to worry about. So we have to be careful about which elements get the delta plus and the delta minus, of course. Delta minus goes to the most electronegative. Delta plus goes to those atoms that are immediately bonded to that more electronegative element, not any others. Now, last step is 3, add our arrow between 2 bonded atoms. Oh my goodness, I actually get frustrated. I rarely get frustrated while I'm grading, but when I see arrows like this, I'm like, I don't know what to do with this arrow because you're showing a dipole stretching across the entire molecule. And that's a pretty weak dipole if you want to go through multiple bonding effects. And it's not what we're asking you to do at this point in the semester. I would rather see you, and by rather, I mean you need to do this for me now. We can worry about the more advanced topics later. Show me a dipole arrow between 2 elements that are bonded with each other, and only 2 elements. So in this first case, I'm going to start at the positive and go to the negative because I have a positive tail. So the positive tail lines up with the delta plus. The arrow then goes towards that more electronegative element. In the second example, we have 2 possible dipole arrows that we could show. We go from delta plus to delta minus, just clearly showing my extension between 2 elements, okay? If you drew the arrow down here, that's probably good enough for me to figure it out. If you draw it like way up here, I can't figure it out. If you draw it like this, and you're like, that's an arrow between the carbon and the oxygen, I'm gonna be like, no, you're kind of just drawing a big arrow over the entire molecule because I can only assume because you don't really understand the concept of the dipole moment and dipole arrows. Okay, last example, I'll go here, positive tail, oxygen with a negative. Okay, so the thing we also need to be able to do is to show this on our bond line structures. So drawing the exact same molecules as bond line structures, always good practice. Okay, so we'd have delta minus Delta plus goes to the carbon atom that in the letter C is not explicitly drawn, though that line indicates we're going from chlorine to carbon. Okay, and that's our dipole arrow. So we have delta minus on the oxygen. I've drawn this, this second molecule in two ways. So we have a delta minus on the oxygen atom in both cases. You can see that putting the delta plus on the hydrogen is really only productive if you show the bond that's connecting the oxygen to the hydrogen atom. So going from carbon to oxygen, we have a delta plus to delta minus in both cases. And I can show a dipole arrow now kind of slanted at an angle from that partially positively charged carbon to the oxygen atom. In the second example, I have more opportunities to clearly display dipole arrows, which is why sometimes it's helpful to draw the OH as an O bond H instead. Last example, delta minus, delta plus. Arrowhead towards the delta minus, partial positive directs where the plus tail will go. Okay, what I want to do just in the last moments is I want to talk about the idea of acidic hydrogens, and I will be quick. I feel like this would be too small for a separate video. And I guess we've started class and I've already committed to only being 2 videos. That's not a good reason to make it longer. Anyway, so acidic hydrogens are hydrogen atoms. You know what? I will just make a separate video. All right, let's call it. Let's see if I can, there. Okay, that's gonna be it for this video. In the next lecture, we'll look at how electronegativity, polarity, and these sort of things will influence things like acid-base reactions.